People have 12 minutes to get here. I'm going to get started. So, chapter 21 homework on WebAssign is due today. The chapter 22 homework is due on Thursday. And the chapter 21 quiz is today in SI. You get one sheet of notes to use for reference. Any questions about any of that? Okay, let's continue. So we were talking about rocks. So the density and composition of rocks, the dark low silica rocks are denser than the lighter high silica rocks because the other components that make them dark are also heavier. The continental plates are primarily composed of the less dense high silica rocks. Therefore, they stand high above sea level. And oceanic plates are composed of more dense low silica rocks, therefore rest lower, usually below sea level. And andesite is the name given to many rocks of medium silica content. So, just a general overview. High silica content rocks, these are light in color, also light in mass. They're low density. If they're extrusive, coming from lava, that's rhyolite. If they're intrusive, forming underground, that's granite. We had both rhyolite and granite in the samples you looked at. There were a couple different granites, and there was also rhyolite. Medium density is mostly dark. Extrusive is andesite. Intrusive is diorite. I can't remember if we actually had any. I think we had some rhyolite. Either rhyolite or andesite. And then low silica content is dark, basalt, and gabbro. And there was both basalt and gabbro in the samples. Number 1 was basalt. No, maybe it was number 2 was basalt. I don't remember off the top of my head. So overall, the continental crust is less dense and thicker than the oceanic crust, which is more dense and thinner. So when magma cools underground and forms some large body of intrusive rock, igneous rock, this is called a pluton, or Pluto, the Roman god of the underworld. Plutons are classified by 2 criteria. How big they are, their size, and the size and shape of the intrusive rock body, and the relationship of the intrusive rock body to the surrounding rock that it penetrates. Is it cutting through that rock, or is it just going between layers? Those kind of things. If it cuts across the grain layering of the surrounding rock, it is discordant. So discordant plutons cut through layers of rock. Some examples of these are batholiths and dikes. And a pluton is said to be concordant if it is parallel to the grain or layering of the surrounding rock. So it goes between the layers of the existing rock. It doesn't cut through them. And some examples of those are sills and laccoliths. Sills and dikes have similar shapes. They're both thin, flat bodies, but sills are between layers of existing rock, and dikes are cutting through layers of existing rock. So sills tend to be horizontal, dikes tend to be vertical. And then batholiths are just big, and laccoliths are sort of, well, laccoliths are structures where they're between the layers, but they fill with magma and it pushes the uprising layers up in a sort of blister-like structure. So here are some examples. So here we have a sill is when, the gap between layers of existing rock gets filled with magma and it cools. A dike is when a fault or joint cutting through layers of existing rock gets filled with magma and it cools. And a laccolith is like a sill, it's between layers, but enough magma is pushed in to squeeze up the layers of rock above it, so it blisters up. And then a batholith is just a big, giant, solid lump of magma cutting through many layers that is particularly large, that solidifies. So a batholith is a large, exposed, discurrent, intrusive igneous body. The big thing about batholiths is they are big. They have an exposed area of at least 40 square miles, or 103 square kilometers. And they originally crystallized slowly at great depth beneath the surface of the earth. These are these big areas that fill with magma and slowly cool. And they only become exposed at the Earth's surface when various forces push them up, or when a very deep canyon is carved by erosion. Something has to get down to where they are to expose them, and they're generally pretty deep. Dikes are discordant intrusive igneous bodies formed by magma that filled a vertical or near vertical fracture. They're basically a vertical sheet or near vertical sheet that flowed through an existing crack, filled it with magma, which then solidified to form a dike. Since most fractures are narrow, the infilling intrusive igneous material hardened into a thin vertical sheet. Of igneous rock, and the size and extent of individual dikes is quite variable because it really depends on the cracks that they fill, the dimensions of the fractures that get flooded with magma. Sills are like dikes, except they're horizontal. So dikes are when you flood a crack up vertically and it cools. Sills are when you flood between layers of existing rock, which is fairly common because sedimentary rock forms in layers. Fill the gap or injected between the layers of pre-existing rock, and you get these thin, flat sheets horizontally. And laccoliths are also concordant and are injected between layers of pre-existing rock, but it's unlike sills where it's just filling the gap. Laccoliths, have a noticeable blistering of the overlying rock layers. There's enough pressure in there to push up the layers above them. And they're structured very much like a blister. A blister is a concentration of liquid in between the layers of your skin. This is a concentration of liquid magma in between the layers of the existing rock. And so they look just like blisters. They're like rounded, domed like blisters. Now, if the magma exits the earth and becomes lava at the surface, that can form a volcano. A volcano is a hill or a mountain that's formed by the accumulation of lava and other volcanic rock fragments that are ejected through some vent in the Earth's surface. Three basic products are ejected from active volcanoes. An active volcano is one that is, emitting stuff. And three basic things come out of volcanoes. Gas, because that magma underground has dissolved gases in it. When it comes to the surface, the pressure releases, those gases stop being dissolved. They leave solution and are released at the surface. So much like when you release the pressure on a soda bottle, the dissolved carbon dioxide exits. When you release the pressure on magma, well, the dissolved carbon dioxide exits. It's one of the things that's in there. There's also the primary gas that's released is water vapor. Then there is lava, liquid molten rock, but they also will emit solid rocks. Because that lava may be carrying along solidified material, or it may be that it solidifies on the way out. It may have been plugged, and that plug may have shattered and broken and be flung out. A variety of things can happen to cause it to release solid material. And that's also how you get things like volcanic ash and dust, which are just, there's tiny pieces of solid material. They're generally formed from droplets of lava cooling down very quickly in the air. Oh, yeah, let's give this a second. So here's a short introduction to volcanic activity. Sorry about YouTube being so slow. So gases are generally constantly extruded from an active volcano. One of the things that people study is sort of what gases are being emitted to see if there's any indication of whether studying how gases are being emitted, how much, et cetera, how that indicates whether there's an upcoming eruption. Because people are trying to figure out how to better predict the eruptions of volcanoes. Another thing we can't predict very well in the short term. So the main gas that gets emitted from volcanoes is just water vapor. But there's also carbon dioxide and hydrogen sulfide, and sometimes that's very unfortunate. There's been a couple cases where volcanoes have emitted large quantities of toxic gases, which are heavier than air. There's been at least one case where a volcano emitted a large quantity of toxic gases heavier than air. It flowed down into a valley where a village was, wiped out the village. I don't remember where that was off the top of my head, but that is something that actually happened. Lava is liquid rock. It's extruded from volcanoes in varying amounts and varying viscosities. Some places extrude a lot of lava that's very thin and easily flowing, like the Hawaiian Islands. Some places have thicker, more viscous lava. It tends to be that thin, low viscosity lava. Well, low viscosity lava corresponds with more peaceful, consistent eruptions. High viscosity lava tends to correspond to more violent, irregular eruptions. So some volcanoes also emit large volumes of solid material. These are collectively known as tephra or pyroclastics. Pyroclastics just means like broken with fire. Tephra is expelled in almost any size, from fine ash and dust up to boulders. It includes material that's initially ejected molten and then hits the ground as a solid as well. So a lot of the ash and dust you get actually comes out liquid, solidifies in the air, and comes down. You can also have lava bombs, which are larger lumps of lava that come out as a big ball. They cool in the air and drop down. They come down round instead of irregularly shaped. And one of the most dangerous things that can come from a volcano is something known as a pyroclastic flow. So that's fine ash and dust emitted by the volcano that gets propelled high up in the air, carried by the hot gases, and then it can fall down and basically flow down the side of the mountain very quickly, like hundreds of kilometers per hour fast. And it's full of boiling hot gases and dust and such. And the ash from volcanoes can be very destructive as well. So pyroclastic, something very, more or less a pyroclastic flow is what buried Pompeii. Little different. There's some complications there, but basically it was suffocated by a cloud of ash and dust from the volcano that's settled down. The volcanoes display two basic eruptive styles: explosive and peaceful or non-explosive. Explosive volcanoes tend to have thick, high silica magma. They go off irregularly and violently. They go boom. They blow their tops. Peaceful volcanoes tend to erupt more often and have less viscous, higher silica magma. So peaceful, constantly erupting volcano would be Kilauea, which has been erupting more, well, on and off, but almost continuously. I think there was like a break of maybe a year in there since 1983. So as long as I've been alive, it's basically been erupting. It did stop a couple of times, but then it started up again shortly afterwards. and it just spews out lava. I mean, there are insanely cool looking lava fountains going on where from the pool of lava in the crater, you can get fountains of lava shooting up, but it's not like super violent. It's just lava. I mean, you have to get out of the way of the lava, but lava doesn't move that fast. It doesn't flow that fast. Yeah. Yeah, eventually they can die. They can run out. So there's lots of extinct volcanoes out there. It's just a mountain. I mean, it's then a solid mountain. So there's a lot of mountains out there that are extinct volcanoes.
Don't, don't we call those dormant volcanoes, ones that are no longer able to erupt?
There are dormant ones, which might return, and then there are extinct ones, which we really don't think will ever return.
Okay.
I might be wrong on the terminology there, but yeah. We, well, I mean, you can get rock solidified from lava. It's not a big, particularly difficult. And if you want to get liquid lava, it's totally possible to literally at some of these volcanoes that are more peaceful, there are researchers who literally go scoop up some lava. I mean, you have to wear safety equipment to do it, but it's not, you can walk up to the edge of the lava because it's a big pool of lava in some of these places. Like Kilauea has a big pool of lava. Sometimes the volcanoes in Iceland are also very fast flowing. And then there are also some research projects where they remelt lava rock, rock from lava to study lava. I don't know what exactly they're saying getting lava. I mean, it's all the thing is that the term lava is also used for the rocks that form from solidified lava. So if it's solid, I mean, also arguably if you just melt rock, you're making lava. Yeah, so there's different rocks when they melt form different kinds of lava. So different magma, the viscosity of different magmas of molten rock is the primary thing that determines the eruptive style, the violence of the volcano. So low viscosity magma flows easily, therefore it's characterized by peaceful eruptions. High viscosity magma has difficulty flowing, tends to stick, pressure builds up, you get more violent eruptions. Magma viscosity is primarily determined by two main factors, temperature and silica content. Luckily, these two factors are actually related. So hot magma is low silica magma, cool magma, cooler magma is high silica magma. So in general, the higher the temperature, the lower the viscosity. Much like honey, you warm it up, it flows more easily. In general, magmas that originate deep within the earth have higher temperatures. They also have less silica content. And then the higher the silica content, the higher the viscosity, the more difficult it is to flow. And in general, magmas that originate at shallow depths have higher silica content and lower temperatures. And it turns out part of the ways that like rock melts, the high silica magma melts out first, then the low silica magma melts out at a higher temperature. So different minerals melt at different temperatures. And so that's part of this process. So rhyolitic magma that is low in temperature and high in silica content is generally got violent eruptions. You generally see this in oceanic continental subduction zones, like the Cascades. So the famous one being Mount St. Helens in the US, which literally blew its top off. It ended up like over 1,000 feet shorter because it blew like the side of the mountain off when it erupted quite violently. And acidic magma is in between, low to moderate temperature. It has medium silica content. It's moderately violent to violent. There's oceanic continental subduction zones and volcanic island arcs are places where you see that. I think Mount St. Helens is somewhere in between these because it's a stratovolcano and those can sort of alternate between the two. And then basaltic lava is high temperature, low silica content, peaceful eruptions. This happens at divergent boundaries where plates are spreading apart. That's pulling the convection currents that drive that process are pulling magma from very deep. And the hotspots, volcanic hotspots are where hot magma is rising up from very deep in the earth, causing volcanoes in the middle of a continental plate, like Hawaii. So the least viscous magma that's currently the least viscous lava that's out there today is in Hawaii. Hawaii has the longest flowing, least viscous magma currently coming out of the ground. So peaceful eruptions involve basaltic magma. Basaltic magmas originate deep within the earth and are therefore very hot. They also have relatively low silica content. And due to the combination of high temperature and low silica content, basaltic magma flows easily, resulting in the peaceful eruptions. Most basaltic eruptions occur in two distinct settings along the length of a divergent plate boundary, like in Iceland, or in isolated areas where a lithospheric plate moves over an unusually hot and stationary zone in the upper mantle, called a hot spot or mantle plume, like Hawaii. There are other hotspots out there. Not all of them have volcanoes. So the other famous hotspot in the US is Yellowstone National Park. It has lots of hot springs and other stuff. There's lots of geothermal energy, but there's not actually any volcanoes forming. And hotspots appear at the surface as a line of active, dormant, and extinct volcanoes. So active volcanoes are active. Dormant volcanoes might become active again, and extinct volcanoes are not going to be active again. So the Hawaiian Islands and the Emperor Seamounts are a continuous series of volcanoes formed over the past 70 million years. So the Hawaiian Islands, you start at the big island of Hawaii, that's the youngest. They get older as you travel along the chain. And then if you look underwater, there's this chain of mountains, extinct volcanoes underwater continuing along that are even older, and those are the Emperor Seamounts. So here's the Hawaiian Islands. This is the big island of Hawaii, where it has Kilauea, the active volcanoes, the smaller islands, and then the chain of Emperor Seamounts getting progressively older. The rising magma from the stationary hotspot in the atmosphere forms volcanoes as the Pacific Plate moves slowly over the hotspot. And you can actually trace this path all the way back to where there was massive volcanic activity millions of years ago in Siberia, the Siberian traps, which may have caused that activity when that hotspot was a lot more active and on the continent may have actually caused a mass extinction. So, yeah. Here's a short video about Hawaii and hotspots. That was not what was supposed to happen.
Hawaii sits in the middle of the Pacific Ocean and nowhere near the edge of a tectonic plate where volcanoes are usually found.
Okay, what just happened? Sorry.
Hawaii sits in the middle of the Pacific Ocean and nowhere near the edge of a tectonic plate where volcanoes are usually found. So how did the island chain form with all of its volcanoes? The island chain is located over a hotspot fueled by a mantle plume of heated rock. Solid rock at the bottom of the Earth's mantle is heated by the planet's core. That hot rock slowly rises and pushes up the crust, forming a bulge. Under that bulge, some of the rock melts into magma. Magma makes its way to the surface through cracks in the crust. Once it's above ground, it's known as lava. Hawaiian volcanoes produce lava flows made of melted basalt, which is more liquid than lava produced by more explosive volcanoes like Mount St. Helens. Basaltic lava flows form volcanoes with gently sloping sides. A lake of liquid lava can sometimes be seen at the top of active volcanoes like Kilauea. Sometimes the magma can flow underground to the sides of the main vent and erupt out of cracks in the ground called fissures. When lava meets ocean, the island grows, but you may not want to get too close. That steam is hydrochloric acid laced with tiny shards of volcanic glass. The Pacific Plate is moving to the northwest, dragging the crust over the hotspot and creating islands as it goes. The hotspot itself might be moving too. The volcanoes on Niihau and Kauai, the northwesternmost islands in the chain, are about 5 million years old. The Big Island of Hawaii is the youngest and started forming about 400,000 years ago. It's still changing and is home to 4 active volcanoes. Eventually, the Big Island will no longer be over the hotspot, and a new island will grow next to it. But maps won't need updating for a while. Loihi won't break the ocean's surface for another 200,000 years, give or take. For Scientific American, I'm Kelsey Kennedy.
Okay. Your name? Okay. So, that was Hawaii, which has some of the more peaceful eruptions. Explosive eruptions generally occur along subduction zones and involve silica-rich magma. And magmas that originate within a subduction zone are not deep and are therefore cooler in temperature. They're also higher in silica content. And due to the combination of lower temperature and high silica content, these magmas can be very viscous, resulting in explosive eruptions. So this is a video summarizing different types of eruptions. From peaceful to explosive, peaceful, covering all types. Plinian, because it also killed the famous person Pliny the Elder, who had gone there to help rescue people from it. And unfortunately, it's finally there. Here's an image of the Mount St. Helens eruption in 1980, which was violently explosive. It blew off the whole side of the mountain. And various volcanic structures form from volcanoes, and different types of magma produce different sorts of structures. So when molten volcanic material reaches the surface of the earth, it creates a number of various expressions. and the type of feature that forms is largely dependent on the composition and temperature of the lava that comes out. So specific and common volcanic structures include things like flood basalts, which are areas that get flooded by molten basaltic lava. It cools, forms solidified rock. Shield volcanoes, which are less steep, less steep, very broad volcanoes that form from basaltic lava. Stratovolcanoes, which are sort of the traditional volcano you think of when you think volcano, tall, steep sides. They form from alternating layers of pyroclastics that get glued together with lava flows. And then there's cinder cones, which are small, steepish volcanoes that are made primarily just of pyroclastics. And then calderas are what happens when the magma chamber that was full of magma, now that it is empty, collapses, causing the area above it to collapse, and that forms a caldera. So fissure eruptions take place when large volumes of lava get extruded from long fractures along the surface of the earth. The place where you can see this happening today is Iceland. So 2010, the eruption of Eyjafjallajökull. I'm certain I butchered that. Had one, you can see these sort of long cracks blowing out lava, and significant portions of Washington, Oregon, and Idaho are covered with a series of ancient flood basalts called the Columbia Plateau. These were enormous quantities of flooding out that was much less viscous than modern lava and covered much larger areas. And the basaltic lava that formed these layers was extremely fluid, high temperature, low silica content, and eventually covered an area of 576,000 square kilometers, with an average thickness of 150 meters. And the actual stack of flood basalts can get quite thick. Gets quite thick. Here's a short video about the Columbia River flood basalts.
Two-minute geology with 2-minute geology.
Hello, young people. The Columbia River basalts near Quincy, Washington. We're at Quincy, Washington, but we could pick any spot between Spokane, Washington, and Seaside, Oregon to do this show. These brown layers of basalt are everywhere in the place where the Ice Age floods did massive amounts of erosion thousands of years ago. There's more than 300 layers of basalt here, 300 separate volcanic eruptions, and the stack of basalt is more than 2 miles thick in places. The lavas started erupting 17 million years ago here and flooded a landscape, buried a landscape in lava. The obvious question is, which volcano erupted? Was it Mount Rainier? Mount St. Helens? The answer is none of those. The Cascade volcanoes do not match the chemistry of these basalt lavas. These are lavas that came from the east. They erupted out of fissures, deep cracks, that emitted Hawaiian-like lava starting 17 million years ago. Fissures that formed related to the birth of a hotspot that's now underneath Yellowstone National Park in Wyoming. The present is the key to the past. To really visualize eastern Washington 17 million years ago, we need to go to Hawaii today. Those Hawaiian lavas today are the same kinds of lavas that we have here. Lava flows in Hawaii, very fluid. The most fluid lavas we have in nature average less than 3 feet thick. Here in eastern Washington, the lava flows average 100 feet thick. In Hawaii, the lavas travel on average 3 miles in length. Here in eastern Washington, many of the lava flows traveled 300 miles. And in Hawaii, 30 miles are covered by a typical flow. Here in eastern Washington, 30,000 square miles of area buried. The Columbia River basalts near Quincy, Washington.
It's all out here to see. Coulees, rocks, and canyons is scenery. Right here for you and me. 2-minute geology.
So here is the Nevada del Ruiz volcano in Colombia, as seen from above. So shield volcanoes are the volcanoes that form from a source that's very basaltic and localized. So lava that's not quite as fluid as the lava that formed flood basalts, but still very fluid. The Hawaiian volcanoes are the classic examples of shield volcanoes. So there's an upwelling magma. That magma comes out and it flows out to the side. They have very gentle slopes and were formed by repeated basaltic flows. Eruptions are generally frequent, but not particularly violent. So for example, killer whale's been erupting pretty much continuously for the last 40 years. But none of them have been particularly violent. I mean, yeah, you're gonna have to move if a lava flow is gonna hit your house, but you can walk faster than the lava flow. Stratovolcanoes are the large classic volcano, the kind of volcano you draw when you think volcano. They're composed of alternating layers of medium and high silica content lava and tephra, and these volcanoes generally have violent eruptions, though they erupt much less frequently than shield volcanoes. And most of the majestic solitary mountains of the world are all stratovolcanoes. So some examples: Mount Fuji, Mount Shasta, Mount St. Helens, Mount Hood. These are all stratovolcanoes. I think also Mount Kilimanjaro is a stratovolcano. So here is Mount Fuji, which is this gorgeous stratovolcano. And the biggest terror of Japan is that if it decides to become active again, pretty much every major city in Japan, most major cities in Japan are within the fallout range of it. It's like
right now.
it is dormant, but it's not certain that it's extinct. And the consequences of it erupting would be very bad. Now, some volcanic features are relatively small. So cinder cones are built when a volcanic eruption is particularly high in gas content, and it basically blows out material which cools into cinders. They emit primarily tephra, so just bits of rock and material, and pile up just in a pile of stuff around the vent. And they rarely exceed about 300 meters in height. So here's a short video about different types of volcanoes. This may cover some.
Volcanoes act up in every possible way. Like a moody person, they can erupt in violence or steam silently, lazily creep along or self-destruct. A volcano's origin determines its temperament. Many volcanoes erupt along subduction zones. Here, the great tectonic plates of our planet's surface push against one another. Along this margin, where one plate is rolled beneath another, we find the most violent volcanoes. Explosive eruptions fit our image of a volcano. They create large, cone-shaped mountains. These erupt when magma below forces its escape. Fueled by expanding gases and boiling groundwater, the excess heat blasts through. Volcanoes like this often have alternating layers of different volcanic materials: ash, cinders, and lava. These layered cones are called composite volcanoes.
Or stratovolcanoes. There are two names for them.
Hawaii isn't near the joining of two plates, but it's a hotspot of volcanic activity. What fuels it? The Hawaiian Islands are hotspot islands, created when a pool of magma breaks through a thin spot in the crust. As it burns through, the plate moves along at 10 centimeters a year. One island is carried away to cool, while the next one is created in assembly line fashion. On the big island of Hawaii, Kilauea has been erupting since 1983 and shows no signs of letting up. It's an example of a second kind of volcano, the shield volcano. The central crater is called a caldera. It still steams, but probably won't erupt violently. Farther out, lava oozes and flows, creating new land as it cools. The wide flow is what creates a shield volcano rather than a cone one. This new unstable bench is pure basalt. Sometimes the flows are only inches from the surface. The thick, honey-like lava, typical of Hawaii, cools into a harsh, barren environment that can take years to support life. Cinder cones are a third kind of volcano. Mexico's Paracutin is a dramatic example. Like composite volcanoes, they can be explosively violent visitors to the surface of our planet. They burst forth with enormous quantities of ash, cinders, and lava fragments. They rapidly build volcanic mountains, but never as wide as shield volcanoes or as high as composites. Cinder cone shape is determined by the size of the ejected material.
So here is the cinder cone in El Salvador. You can see it's very steep, but it's not huge because it's basically just a pile of rocks that got blown out of the, tephra, rocks, dust, small material. And the size is determined by, the height of the cinder cone is really determined by the size of the material. And the steepness is determined by the size of the material because it's just, this will pile up as steep as it gets before stuff starts rolling down the slope. Much like piling up a pile of sand. There's some angle that it will pile up at. You can have, it's more the other way around. A volcanic eruption can cause earthquakes, but generally earthquake. So there were a lot of dramatic movies about earthquakes in California causing volcanoes. That's not going to happen. It's the wrong kind of plate boundary. So at a transform plate boundary like you see in California, you don't get any subduction, you don't get any magma to form volcanoes. So that is unlikely. Now a caldera is what happens, is a large, roughly circular steep walled depression at a volcano summit. Lots of volcanoes have calderas. And they result primarily from the magma chamber underneath that was full of magma. All that magma gets pushed out. Then that chamber is kind of empty and it collapses downwards. And a dramatic example, that doesn't mean that the volcano is extinct. The example we're going to show here is Crater Lake in Southern Oregon, which is amusingly not a crater, but it is well, it's not an impact crater. It is a caldera. It occupies the caldera that's formed by the collapse of the magma chamber of a once active stratovolcano, but it's just dormant. Because Crater Lake here, this is Crater Lake, it occupies the caldera at the top of Mount Mazama. This is Crater Lake. See here, this little island? That's Wizard Island. That's a cinder cone that formed from activity after the caldera collapsed. So there's still some activity going on there. There's also a cursed stump floating around in Crater Lake, which apparently if you tie it up, the weather gets bad. So, yeah, that's Crater Lake. So here are some examples of some historic eruptions. So Mount Tambora in 1815. Mount Tambora is in Indonesia. It was volumetrically the largest volcanic eruption to occur in written history. And so much volcanic dust was put into the upper atmosphere that the sun's energy was partially blocked, leading to 1816 being an unusually cold year. Specifically, it was called, particularly in Europe, because of the way the air currents flowed. Particularly that year was called the year without a summer. And there have been certain consequences of that year. This volcanic eruption may be responsible for modern science fiction because Frankenstein was written because the year without a summer was so miserable that Mary Shelley and her friends on a vacation didn't want to go outside, so had a writing contest in which Frankenstein was written, and also the first modern vampire novel.
Basically, what you're saying is that that volcano never erupted, Frankenstein would not be a thing.
Maybe.
Probably not.
I don't know. I mean,
It's plausible.
it's a plausible argument. There's also a plausible argument that Mary Shelley would have said that, I don't know. That was a crazy group of people. Mount Pelee erupted in 1902. It's located on the island of Martinique in the Eastern Caribbean. It blasted out a deadly cloud of superheated volcanic gas and tephra that killed over 30,000 people. Paracutin, located in Mexico, erupted in 1943. Began as hot gases were emitted in a plowed cornfield. So it was just cornfield. Hot gases started coming out. And the cornfield was destroyed as the volcanic cone eventually rose over 400 meters in height. Some poor sod had his cornfield turned into a cinder cone. Surtsey in 1963, located off the coast of Iceland. This volcanic eruption eventually formed a permanent new island in the North Atlantic. The Sophia Hills in the 1990s, located on the Caribbean island of Montserrat. This volcano had been dormant for 400 years until it began spewing ash in 1995. And the capital city of Plymouth and the airport were buried in 1997. And basically, most inhabitants left the island or moved to the north end. It rendered most of the island uninhabitable. Mount St. Helens in 1980 is a stratovolcano located in southern Washington that had been dormant since 1857, and they had not been expecting it to go. This eruption devastated more than 400 square kilometers of area, resulted in the largest volcanic eruption in I think in the U.S. in recorded U.S. history.
Mount St. Helens erupted since.
I don't think so. And it resulted in the death of more than 60 people. And it was big. Like they didn't expect this eruption to be as big as it was. They saw some warning signs of more eruption, but they weren't expecting it to be anywhere near as big as it was. And because of basically a freak accident, it got recorded on film. It was filmed. Mount Pinatubo in 1991 in the Philippines propelled ash into the atmosphere to a height of over 24 kilometers. It destroyed thousands of acres of cropland enforced the abandonment of the Clark Air Force Base. And I think there's a more recent one in Indonesia that basically just blew up an island. So you can get tsunamis from violent volcanic eruptions. Now, why do people continue to live in the shadow of a dangerous volcano? So an eruption by Mount Vesuvius in 79 CE buried the 2,000 residents of Pompeii. And that was one of several towns that were destroyed by this volcanic eruption. Yet Naples, the large and growing Italian city of Naples, is only a few kilometers from Mount Vesuvius. There's a city there. Part of this is because the soil derived from volcanic ash, the soils from volcanic ash are rich and fertile. They result in extremely productive agricultural areas. Naples is famous for its tomatoes, and much of Southern Italian cuisine uses lots of tomatoes because the area around Naples, part of that, is tomatoes grow extremely well there in the volcanic soils. So it's a trade-off because irregular things that happen once in a while, well, it happens. So here are some examples of 10 volcanic eruptions that were caught on camera. So these are more recent ones.
Volcanoes are scary unless you're immune to lava, ash and falling rock, in which case you're probably not scared by volcanoes. For the rest of us though, they're pretty crazy events to witness. Most of us haven't seen a volcano up close, but thanks to other people and their cameras we're able to see videos of their immense powerful eruptions. We have the best of those for you guys today. My name is Danny Burke and this is the top 10 volcanic eruptions caught on camera. Starting up at number 10 now we have Pu'o'o. This is an active volcano in Hawaii, and in 2014 a lava flow started shooting out eastwards. Roads were closed off as the flow devastated everything in its path. Now, despite numerous defensive measures being taken, it seemed like nothing could halt the slow but steady progress of the lava. This resulted in this incredible footage of the lava burning through a metal fence and then right onto a road. Alright, at the number 9 spot now we have the Sakurajima volcano. This volcano in Japan erupted in February 2016 and some incredible footage was taken of it. The eruption itself was already quite large, sending lava and rock tumbling down the mountain just 30 miles away from a nuclear power plant. However, many people were more amazed at the lightning storms that formed inside the clouds. Lightning and lava, definitely a cool but lethal combination. Next up at number 8 now we have Mount Tavuva. This volcano in Papua New Guinea erupted in 2014. Some tourists were nearby and captured the footage you're about to see. They expected the eruption was going to happen at any moment. They expected that a sonic boom would follow shortly after, but maybe not as loud as this. Next up at number 7 now we have Popocatépetl. This is an active volcano located just southeast of Mexico City. It erupts every few years, and when it did in September 2017, cameras were there to capture it. The rocks it spewed out were found more than half a mile down the slope, as well as ash over nearby towns. Scientists monitor the volcano carefully as 25 million people live within 60 miles of it. A super eruption could be devastating. Alright, at number 6 now we have the Turrialba volcano. This is located in Costa Rica, and the footage you're seeing comes from an eruption in September 2016. It was caught by a research team's cameras, and the footage sped up to show you just how long the volcano was spewing out hot ash. This event consisted of 4 separate eruptions, which led to the closure of the capital city's international airport. It was reported that clinics were filled with people suffering from skin and lung irritations. Some stores even started selling kits with goggles and masks for protection. Moving on to number 5 spot now we have Mount Shindaki. This volcano in Japan erupted erupted in 2015. It was largely unexpected, but amazingly, an internet webcam caught the whole thing live. Huge waves of pyroclastic flows cascaded down the side of the volcano, spewing rock fragments and hot gases across the volcano's northwest shore. Japan's meteorological agency raised their alert level to 5 and ordered the island's 140 residents to evacuate. Okay, next up at the number 4 spot now, we have the Mayon volcano. This volcano in the Philippines has been known to erupt from time to time, but the most recent event might have produced the most incredible footage so far. On January 22nd, 2018, an alert level 4 was raised as Mount Mayon spewed ash 3 kilometers into the sky. The footage you're seeing right now was taken at night, where lava bombs and rockfall produced a spectacular sight. Now to my eyes, the volcano seems to resemble something like Mount Doom more than anything I've seen in real life. Incredible stuff. Okay, moving on to the number 3 spot now, we have Journey to the Center of the Planet. This clip comes from a BBC documentary of that name, where a scientist in a protective suit ventures to the edge of a volcano's lava lake in order to try and get a sample. Things get a little bit too close for comfort when the lake starts to erupt over the edge, spilling lava everywhere. The scientist has just enough time to get out before lava flows where he was stood just minutes before. Okay, next up at number 2 now guys, we have Mount St. Helens. On May 18th, 1980, Mount St. Helens in the state of Washington erupted. It's often referred to as the single most disastrous volcanic eruption in US history. The whole north face of the volcano just slid away to expose an explosion of molten gas and rock that spread out over 11 different US states. This is the incredible footage from that day. Although some scientists were aware that the volcano was showing increased signs of activity, everyone was surprised at the sheer scale of this eruption. And finally at number 1 now, we have the Kilauea volcano. Located in Hawaii, it's also referred to as the volcano that never stops erupting, and that is kind of true. The volcano has been erupting since 1983, but things picked up a notch on New Year's Eve 2016 when a lava delta collapsed, taking part of the sea cliff with it. This created a constant flow of lava into the sea below, which has been captured by a number of people, including this footage you're seeing now from the Wall Street Journal. Well, that was fascinating. I always end the video by saying well, don't I? Does anyone else notice that? Anyway, do you like volcanoes?
So, regarding Kilauea, it has stopped a couple of times. And then it stopped in 2018 and then started up again in 2020 and then stopped again a couple of times since then. But never for more than a year or two. Ugh. And it's active right now. And spewing out dramatic lava fountains. So James Hutton's rock cycle model was originally derived from his field observations of modern sedimentary processes and ancient rocks. And during his frequent trips in and around Scotland, he observed that normal everyday effects of water and wind on rocks and soil. And in particular, he noted that mud, sand, and rock fragments of all sizes were weathered and carried by streams from high areas to low areas. Weathering is the process by which rocks get broken down. So here is a short video about weathering and erosion, particularly freeze-thaw cycles, which is the primary method of weathering around here.
Believe it or not, the rolling countryside of Cornwall in southwest England used to look more like the Himalayas or the Alps. Mountains don't last forever. They gradually wear away at a rate of about 10 centimetres every 1,000 years. So all that's left in Cornwall today is a series of domed shapes, giving the landscape its rolling appearance. Changes in temperature from day to night and the expansion of freezing water cause rocks to wear away. When water enters a crack in a rock, it expands as it freezes overnight. When the ice turns to water and freezes again, it forces the crack open a little more. As the water seeps even further, the crack widens. This freeze-thaw action is repeated. It eventually causes pieces of rock to break off. They fall down the mountainside, where they lie as pieces of jagged rock known as scree.
And this same process is also what causes potholes around here. So when rocks break down into pieces, they form sediment. So particles that are eroded from one place are later deposited as sediments somewhere else, usually along rivers, lakes, and at the shore or on the seafloor, because the primary thing that carries along these sediments is water. And Hutton also observed that layered rocks in the highlands that were composed of cemented sand and other rock fragments, and he called these sedimentary rocks because they were formed of sediment. So sedimentary rocks are deposited. He realized that they were deposited in horizontal layers or strata, and older layers converted into sediment are converted into sedimentary rock as they get compacted by the weight of the overlying and successively younger layers. This is what's known as the principle of superposition, just things piled on top of other things. Later, some of these sedimentary layers are pushed up by various forces within the earth to form mountain ranges, and the process continues as the new uplifted areas are affected by weathering and wear away. Now, sedimentary rocks only compose about 5% of the Earth's crust, but they're exposed over about 75% of the Earth's surface. The Earth's crust is dominated by igneous and metamorphic rocks, with sedimentary rocks forming a thin veneer of a few kilometers on top. And lots of the necessities of modern life come directly from sedimentary rocks, to the point where we've developed the technology to basically make artificial sedimentary rock to build our buildings. That's what concrete is. Basically, fast artificial sedimentary rock. Things like petroleum, coal, a good amount of metal deposits used in the construction industry all come from sedimentary rock, as does what we make drywall out of, things like that. In fact, the most common source of iron in the modern day is from a sedimentary rock. Just the most commonly used type of iron deposit. There's a whole bunch of different iron ores out there, but the current most commonly used, most profitable one, at least in the US and I think internationally as well, happens to be a sediment. Some of the most picturesque spots on Earth are also composed of sedimentary rocks. Part of this is because sedimentary rocks can occur in a number of varieties and colors. And because they come in layers, you get sort of striping, and then they can wear away at different rates, and you can get dramatic things. So the Colorado Plateau of the southwestern US offers a particularly outstanding display of sedimentary rocks and their various erosional products. And because that whole area was uplifted, it has some interesting geology. So the process by which sedimentary rocks are formed is called lithification. This is the process by which sediments get compacted and cemented together. And that's the primary process for lithification. And the three things that act sort of as cementing agents or glues are calcium carbonate, silica, and iron oxides dissolved in groundwater serve as the dominant agents for cementing sedimentary rocks together. So in concrete, cement forms into calcium carbonate when you add water, basically. So the weight of the overlying sediments forces the sediment grains together, causing physical changes in the process of compaction. And dissolved minerals will then precipitate out of groundwater, and their growth glues the sediment grains together into a solid rock. Now, sedimentary rocks can be classified according to the origin of their constituents. There's two main types of sediments. There are clastic sedimentary rocks, which are made of little pieces of existing rock, the detrital rocks. And there are chemical sedimentary rocks. So clastic sediments originate from little pieces of rock, solid fragments, detritus that erode from pre-existing rocks. Chemical sediments originate as dissolved minerals in solution. So, if you want an example of what it looks like for chemical sedimentary rocks to form, dissolve some salt and water and then boil away the water. That's or lime scale in your bathroom. That's, a chemical sedimentary rock. Mhm.
Like when you're on the highway and it's like a big old hole.
Where they cut the road through something, it's called a road
yeah,
cut. Uh,
I think it's like a quarry, isn't it? It's a long, I think it's on, now, I think it's on 294, I wanna say. I don't remember, I know what you're talking about, but I just don't remember what,
I'm
I
not
think it's-
sure.
it looks
Well,
like a-
okay.
I think it's a
we're-
quarry.
It is 9:45, so I guess we're done for the day. We'll continue on with this.
I think I know.
I'm gonna stop sharing.